Hi, a very cheerful morning to everyone. We welcome you all for today's webinar, which is LPDDR5 5x from speed to efficiency, unveiling the next era of performance, brought to you by TrueChip Memory Team. In today's webinar, the agenda will be as first, we will discuss about LPDDR overview, then how does LPDDR act as a power saving SDRAM, how LPDDR is different from DDR, LPDDR memory consumption in mobile devices, evolution of LPDDR, also why there is a need for dual channels, covering LPDDR5 features, applications and future expansion, enhancement of LPDDR5X from LPDDR5, and at last about TrueChip VIP and TrueEye GUI. So let's start with a brief overview of LPDDR. LPDDR stands for low power double data rate. So basically it's a synchronous dynamic random access memory, which is also called SDRAM, which transfers the data on both edges, which makes it even faster than the normal SDRAM devices. LPDDR came into the picture in 2008, which was the first version of LPDDR, mainly targeting the mobile industry, and was also called as mobile DDR or the MDDR. These days, LPDDR RAM has came up with a great performance solution for mobile devices due to its narrower channel width and several low power operating states for data transfer. One of the key features of LPDDR is that it achieves a good balance between transfer rate as well as in the cost. LPDDR technology is developed independently of DDR standards in terms of performance, battery life, and data transfer rates. As it was targeted for mobile devices only, that's why data transfer was clocked with a low frequency in low voltage in comparison to DDR RAMs, which makes battery life even more long lasting for mobile devices. Generally, the main question arises, how does LPDDR act as a power saving SDRAM? The power saving in LPDDR can be achieved by using reduced voltage signaling. For example, having the minimum differential input voltage for the clock and write clock in all the supported clock rates, and also the operating voltage of VDD getting lesser than the previous generation of LPDDR. For example, 1.1 volt in LPDDR4 and 0.5 volt in LPDDR5X. Reduced input-output capacitance for CK, CA, DQ and DQS signals, etc. Optional bus termination based on speed, so that the bus termination can be off at lower speed and on at higher speed. Reduced width shared command and address bus, for example, where LPDDR3 CA bus was 9-bit wide and from LPDDR4 devices onward it is 6 or 7 bits wide. Low power standby modes. We have faster entry and exit into standby modes. Power saving can also be achieved by faster and less complex frequency change operation, also called as FSP change procedure, which changes in voltage swings and termination values without ever being in an untrained state, which could result in loss of communication to the DRAMs. Frequency set points allow the LPDDR SDRAM CA bus to switch between two different operating frequencies. This is accomplished by duplicating all CA bus mode register parameter as well as other mode register parameters commonly change with operating frequency. Having the temperature aware refresh method whose status can be read via mode register read command. Going forward, let's see why there is a need for LPDDR when DDR is already present. Now we will talk about how LPDDR is different from DDR. If you are familiar with DDR1, DDR2 and DDR3 devices, which were intended really to live on a DIMM, so most of the PC and laptop contains DDR2, DDR3 and DDR4 devices on a DIMM. And the idea is that there are a lot of memory devices connected to each bus, typically 64-bit wide. There are longer interconnects because the DIMMs are interconnected to the SoC over circuit board, hence in resulting consuming more power than LPDDR. Whereas the LPDDR tends to have fewer memory devices connected in each bus on SoC, with a shorter interconnect with the DDR devices. Though LPDDR devices are placed directly on the top of application processor that they connect. This tends to provide a lower power interface with the power comparison to the DDR devices. This makes LPDDR differs from DDR in terms of performance, battery life, and hence data transfer. LPDDR SDRAM is also designed to be able to scale down the refresh rate of the memory based on the temperature surrounding it via the mode register, while standard DRAM cannot achieve this much scaling. LPDDR SDRAM has the half-channel bandwidth of DDR SDRAM for data transactions. As you can see on the bottom left hand side, there is a shouldered unremovable LPDDR SDRAM. On right hand side, we can have removable DDR SDRAM. So from the graphical representation, we can also see how LPDDR generations are different from DDR generations in terms of voltage supply. LPDDR1 is slightly modified form of DDR1 SDRAM with several changes to reduce overall power consumption. More significantly, the supply voltage is reduced from 2.5 volt to 1.8 volt. Same for LPDDR2 is slightly modified form of DDR2 SDRAMs, where the supply voltage is reduced from 1.8 volt to 1.2 volt. Whereas in DDR3, the voltage is reduced to 1.5 volt, but in LPDDR3, it remains the same at 1.2 volt as in LPDDR2. DDR4 is reduced to 1.2 volt and LPDDR4 to 1.1 volt. DDR5 works on the supply voltage of 1.1 volt and LPDDR5 on 0.5 volt. LPDDR devices have been always a great option in terms of power consumption and with respect to DDR. The memory consumption of LPDDR SDRAM in mobile devices or any other devices looks something like this. It is estimated that 90% of the time the mobile or tablet would be off in low speed mode. We are considering that only a single channel of memory is active and the phone will be typically in dark mode or in your pocket or at the desk, and at that time it is maintaining cell contacts, receive texts, or either receive and display notifications, emails, or to just show the clock time and sometimes the other background activities. 9% of the time memory will be operating in speed ranges from 200 to 3200 Mbps, and within this range we can see we can do a lot of stuff, like we can do texting, we can make calls, we can do surf to internets, reading, and play simple games in which too much of processor of memory is not required and it's not used in its full potential. And then there is that 1% of time where LPDDR full potential is working and actually needed. And there we are actually capturing videos in HD 4K resolution, and also really high graphical intense game or image processing can be done. So here is the summary. We can call 90% to be as power focused mode, 9% to be as best performance under low speed power limits, and 1% to be as performance, or we can say the quality mode. Hence, the 1% of time is only when a real replacement cycle is needed in mobile phones with respect to other memories of LPDDR. Further discussing about the evaluation of LPDDR devices. Each year when a new version of LPDDR devices is launched, the supply voltage decreases, making less power consumption with respect to its last version. If starting from LPDDR1 having 1.8 volts to LPDDR5X working on the supply voltage of 0.5 volts. as the nature of DDR write-read transaction to the memory where data will be sent to the LPDDR memory on negative as well as positive edge of the clock, the data transfer rate will always be double the total clock frequency. As the voltage is decreasing, clock frequency with each new version of LPDDR devices is increasing, making the data transfer rate even higher. For LPDDR1, clock frequency of 200 MHz have data rates of 400 mega transfer per second, and for LPDDR5X having clock frequency of 4267 MHz having data transfer of 8533 mega transfer per second. The command and address signal bit are also decreasing with each version of LPDDR devices. Talking about the prefetch architecture, as we know, the DRAMs with the internal clock are always clocked with a low frequency with respect to the actual bus interface clock frequency, because memory is very sensitive and will have power and data loss if operated in faster bus interface frequency. That's why memory uses a prefetching architecture to deal with the data storing from the LPDDR bus interface to its own memory. Hence, with each version of LPDDR memory, it is enhancing its prefetching size. Starting from LPDDR1, where it was just 2N focusing 2 bytes, and the latest one LPDDR5X is prefetching 16N focusing 16 bytes from the bus interface. Having multi-channel support and with multi-rank configuration, it is even more possible to cover more memory density from 2 GB in LPDDR1 to 32 GB in LPDDR5. The support of multi-channel came afterward LPDDR3. Now let's talk about the need for the dual channels. From the LPDDR4 specification onwards, the aim is to double the data rate over the last generation and to save energy consumption for mobile devices. Compared to LPDDR3, LPDDR2, LPDDR1, which was only a single channel per memory die, LPDDR4 RAM for mobile devices was redesigned for 2-channel die with 16 bits per channel and total of 32 bits, which covers more density than single channel, and also it lowers the core power and increase the efficiency of data transfer. All thanks goes to the shorter path which improves operational speed. From the figure you can see in LPDDR2 and 3, if the data is driven from a particular bank, it will be covering the long path to reach out the DQ signal. But in LPDDR4 onwards, each channel bank data will reach out to the DQ signal faster due to ease of shorter path available and the availability of more DQ signals for each channel. It also lowers the nominal operating voltage from 1.2 volt to 1.1 volt. Here we are showing 4 different possible ways that dual channel or multi-channel are used and works if we have 2 DRAMs available for LPDDR data transactions. The first one is very familiar configuration if used the DDR models in the past. The first one is the parallel, or we can say lockstep model. In this parallel lockstep configuration, we have 2 DRAMs of 2 channels of LPDDR. They are connected to the same command address bus, same chip select signal, but each will have an independent data channel. In this parallel connection, both of the DRAM devices are receiving the same command address, but also they are transmitting data over different byte lanes. Hence, here each of the DRAMs is storing different data and transmitting the same on data lanes while a read command. For example, if transmit a write data with write command having pins as a size of 16 with data bus size of 64 bits, in a single write, 32 bits data on a single clock edge will be stored in the first DRAM and rest 32 bits on the other DRAM. Both the devices are accessed simultaneously. In the second diagram, it is also possible to connect the DRAM devices in series configuration. In this configuration, both of the DRAM devices are connected with the same command address and same data lane, but both are accessed with different chip selects, which is also called as multi-rank configuration, where both DRAMs receive the same commands and address and transmit data over the same byte lanes. And chip select signal determine which device has been accessed one at a time. Looking further in the third diagram, we have multi-channel architecture. This was really popular after LPDDR4 devices, where we had independent 2 command and address signals, 2 chip select signals and 2 independent DQ signals for transaction for each channel of LPDDR DRAM devices. Hence here, unlike in parallel lockstep mode where 64-bit data was separated out for each DRAM, we can store whole 64 data bus size data in each DRAM in single clock edge. Here, each DRAM can operate independently and each other. For example, one channel DRAM might be in self-refresh standby mode and other channel DRAM might be receiving an activate command. At last, in the fourth configuration, which is multi-channel with shared CA bus, both the DRAM devices receive the same command address, but unlike the series implementation, it is up to the chip select to determine which DRAM device to work on particular clock cycle. Here, each DRAM will be transmitting data independently to each other. So both the DRAM here can be in different state but receives the same command. Now let's talk about LPDDR5 key features. So the first feature is the bank architecture. LPDDR5 and LPDDR5X SDRAM supports multiple bank architecture to provide optimal access methods for varied system configurations. The native bus lanes determined by data prefetch sites depend on which bank architecture is enabled. LPDDR5 supports various bank architectures which are as follows. 8B mode, which consists of 8 banks, as this mode doesn't consist of bank groups and only supports bus lengths of 32. 8B mode suppose is only present in LPDDR5 SDRAM and not supported in case of LPDDR5X SDRAM. Along with that, 8B mode supports only 2:1 write clock to clock ratio. It supports maximum data rate of 3200 Mbps. Now you can see on the diagram how the architecture of 8B mode is being designed. In this diagram, there is a CA bus and there are 8 banks distributed for DQ bytes data. Talking about 32 bus length data on X16 pins where total data to be stored is 512 bits, out of which 256 bits will be stored by DQ byte 0, where 256 bits will further be divided into two groups of 128 bits, which will be stored inside memory banks, and another half of 256 bits will be stored by DQ byte 1 inside memory bank in the same manner as DQ byte 0. 16B mode, which consists of 16 banks, as this mode doesn't consist of bank groups and supports both bus lengths of 16 and 32. Along with that, 16 mode supports both 2:1 and 4:1 write clock to clock ratio. It supports maximum data rate of 3200 Mbps. Now you can see on the diagram how the architecture of 16B mode is been designed. In this diagram, there is a CA bus and there are 16 banks distributed on DQ bytes data. Talking about 16 bus length data on X16 pins where the total data to be stored is 256 bits, out of which 128 bits will be stored by DQ byte 0 and another half of the 128 bits will be stored by DQ byte 1 inside the memory bank. Bank group mode, which consists of 4 banks and 4 bank groups and supports both bus lengths of 16 and 32. Along with that, bank group mode supports both 2:1 and 4:1 WCK to CK ratio, which we will discuss in upcoming slides. It supports maximum data rates of 6400 Mbps. Only bank group mode can support burst length 32 in interleave fashion in case of 4:1 write clock to clock ratio. Now you can see on the diagram how the architecture of bank group is being designed. In this diagram, there is a CA bus and there are 4 banks and 4 bank groups distributed for DQ bytes data. Talking about 16 bus line data on X16 pins, where the total data to be stored is 256 bits, out of which 128 bits will be stored by DQ byte 0 and another half of 128 bits will be stored by DQ byte 1 inside the memory bank. Talking about more features of LPDDR5, command and address signals are latched on both the rising and falling edge of the clock, which is of 7 bits. It supports 2 write clock to clock ratio, that is WCK to CK ratio, which are as follows. First one is 4:1 ratio. In this, write clock frequency will be 4 times faster than the clock frequency during the write and read operation. Second one is 2:1 ratio, in which the write clock frequency will 2 times faster than the clock frequency during the write and read operations. It also supports various device modes, such as the first one is X8 mode, in which either lower byte or upper byte can be selected depending on per channel as when this mode is enabled. ODT CA, CS, CK is disabled and is supported by all bank architecture. The second one is byte mode, which allows higher density such as 32 GB devices with 4 8 GB DRAM dies, with each DRAM die supporting only a byte from both channel. The third one is the X16 mode, which the default mode which is being to perform all operations and supported by all bank architecture. It also supports multiple frequency set points FSP, as LPDDR supports 3 FSP, which allows the CA bus to switch between 3 different frequencies with changes in voltage swings and termination values. Then comes the WRX operation. As all previous generation LPDDR DRAM devices supports write operation and multi-write operation, only where LPDDR5 comes with an addition with of WRX operation, as this write operation reduces the power consumption in case of repeated data patterns. It can be operated to an activated bank without WCK to CK synchronization and data input to SDRAM DQs. But it doesn't mean that it doesn't work in case of WCK to CK sync state. It also supports single-ended mode for clock and write clock and RDQS, which reduce the power and increase efficiency in case of various operations. It also supports the write data copy and read data copy function, which reduces the input-output core power consumption by utilizing data patterns repeatedly per 8 byte data copy. It applies to the write and read operation. Now comes the write operation of LPDDR5. As in the case of LPDDR5, there is an enhancement in the case of data transaction from previous generations of LPDDR, as data will be driven on the basis of write clock, not on the basis of data strobe, that is DQS signal from LPDDR4. So before moving ahead for write operation, there is a need for activate command to activate a particular bank in order to access. So you can see there is a differential clock signal, that is CKT and CKC, chip select signal, that is CS, command and address signal, that is CA, differential data clock signal, that is WCKT and WCKC, bidirectional signal, that is DQ, and DMI, which is data mask inversion. So LPDDR5 SDRAM is required to be in WCK to CK synchronization state before write operation. which is error-free latency control. The latency control circuit must know whether the SDRAM is aligned with CK state or not. An LPDDR5 SDRAM is able to detect its state by process called WCK to CK synchronization. When an SDRAM controller issues a cache command with the bit of WCK to CK synchronization, the controller provides the SDRAM with half frequency WCK pulse to relax ISI and the timing margins. So at T0 you can see there comes a cache from which there is timing start name as WCK ENL underscore write, after which WCK starts its functionality as the timing is programmable. After cache command at T1 there comes write command, as the write commands needs to come immediately after cache command. For write operation, WCK must be driven at least TWCK pre underscore static plus TWCK pre underscore toggle. Before that, the write DQ burst. As WCK start toggling for 2 clock cycle in 2:1 WCK to CK ratio, which can be adjusted either in 4:1 or 2:1 depending upon the mode register. From the write command, that is T1, the write latency is defined from the rising edge of the CKT, starts from the rising edge of the clock. The first data comes after the write latency and other delays after the rising edge of CKT of a write command. Bus data is captured by the SDRAM on successive edges of WCK until 16 or 32-bit data burst is completed. After a burst write operation, 1 clock plus TWR must be satisfied before a precharge command to the same bank can be issued in order to close the bank. So here comes the read operation. As mentioned in write operation, bank must be active before write operation. It need to be active in case of read operation as well. As mentioned before, with all the signals in write operation, there is an addition of differential signal RDQS-T and RDQS-C, which are the read data strobe signals that are used in case of read operation. So read operation also requires the same WCK to CK synchronization state before read operation. So at T0 you can see there comes a cache command from which there is a timing start named as TWCKENL underscore read, after which WCK starts its functionality. After cache command at T1 there comes read command, as the read commands need to come immediately after cache command. For read operation, WCK must be driven at least TWCK pre underscore static plus TWCK pre underscore toggle before the write DQ bursts. As WCK start toggling for 2 clock cycle in 2:1 WCK to clock ratio, then it can be adjusted either in 4:1 or 2:1 depending upon the mode register. From read command, that is T1, the read latency is defined from the rising edge of the CKT that starts to the rising edge of CKT from which TWCK to DQO is measured. RDQS also start toggling after T-pre, which is RDQS preamble. The first valid data is available after read latency and other delays after the rising edge of CKT of the first read command. Burst data is captured by the SDRAM on successive edges of RDQS until the 16 or 32-bit data burst is complete. Now here comes the applications. LPDDR SDRAM used in mobile and automotive devices such as tablets and smartphones. Used to maintain battery life. LPDDR memory is highly used in gaming industry, for example, in games like PUBG, Free Fire, etc., and provides high efficiency as compared to other DRAMs. Now let's talk about the future expansion. LPCam, which is low power compression attached memory module. It is a groundbreaking technology that has the potential to redefine the DRAM market for PCs, laptops, and possibly even data centers. LPCam tackles the limitation of SODIMM by offering higher capacity modules that scale from 16 GB to 128 GB. LPCam is a detachable module offering enhanced flexibility for PC and laptop manufacturers. It is promising up to 50% improvement in performance and 70% in power efficiency, all the while occupying 60% less space on the motherboard compared to the SODIMMs, which is in case of DDR. LPDDR6 is expected to come with a data rate of 17,000 mega transfer per second. Enhancements of LPDDR5X from LPDDR5. LPDDR5X support all speed grades and speed pins of LPDDR5 along with the new speed grades added up to the 8533 mega transfer per second, which provides a boom to the mobile industries. It supports bank architecture as follows. First one is 4 bank with 4 bank group, and second one is 16 bank, which is 16B mode. It has customizable mode register to switch between LPDDR5 and LPDDR5X as compared to LPDDR4 devices. Supports clock frequency up to 4267 MHz, whereas LPDDR5 has only 3200 MHz. Now, let's talk about how we can verify LPDDR design using a TrueChip integrated VIP. Here you can see the architecture of LPDDR5 TrueChip VIP. From the left hand side, it starts with the sequences with basic plus error injection test cases block, through which transaction of AXI is transmitted to AXI master and transaction of AHB and APB to APB and AHB master, which are in sky blue and dark blue colors. From this to master, transaction is transmitted further to AXI APB AHB converters via AXI interface and AHB APB interface depending upon the signals. As AXI interface is also connected to two components, the first one is the AXI monitor, which works as a protocol checker and shoots the error in the case of protocol violation. The second one is the AXI scoreboard, which is used to check the integrity in case of writing and reading. Along with that, the APB interface is also connected to the APB monitor, which works as a protocol checker and shoots the error in case of protocol violation. Once the transaction is received by the AXI APB AHB converter, it will convert the transaction in LPDDR5 form, which is a light purple color, through which the transaction is being transferred to the memory controller, which is also in light purple color via protocol interface. Through the memory controller, transaction will go further to DFI5 through DFI interface. And from DFI5 transaction will go further to memory, or we can say LPDDR5 memory via LPDDR5 interface. As DFI interface is also connected to two components. One is the DFI monitor, which acts as a protocol checker and shoots the error in case of protocol violation. And the other component is the DFI scoreboard, which checks the data integrity not only for the DFI interface but also for the LPDDR5 interface, as either data which was in DFI interface and transmitted from DFI5 either same or not, and vice versa. For LPDDR5 interface is also connected to two components. One is the LPDDR5 monitor, which act as a protocol checker and shoots the error in case of protocol violation, and other component is the LPDDR5 scoreboard, which checks the data integrity. Through the LPDDR5 interface, transaction is transmitted back to DFI5 and from DFI5 to memory controller via DFI interface. from which it goes to the converter via protocol interface, which converts the AXI, AHB, APB formats and transmits further to the AXI and APB interface. For integration perspective, integration can be done in an easy manner for each component. Let's take an example. Memory controller. The user can add its DUT controller in the TrueChip environment just by disabling the TrueChip memory controller and enabling their own DUT with a signal connection integration. Integration can also be performed in user test bench by adding TrueChip controller with a signal connection. The same thing can also be done for the PHY and memory as well. Now let's talk about the TrueChip VIP features. Below are the differentiating features of the TrueChip VIP model. First, provide configurable clock skews. Support weightage based randomization in case of generating transactions. Skip initialization process in case the user wants to perform direct write and read without any power up initialization or any other training. TrueChip VIP can do that as well. Individual and independent components, passive monitor as well. Easy enabling and disabling of component as per the requirement. Integrated environment of LPDDR with AXI, AHB and APB. Build coverage analysis for the whole LPDDR5 which covers all features. Support static as well as dynamic error injection scenarios. Supports protocol checker that shoots error in case of violations. Supports dynamically configurable modes. Now here comes the TrueChip patent TrueEye GUI, which is a TrueChip graphical user interface through which user can easily perform integration, easy debugging and easy searching regarding the VIP required field. Example time, easy error detection and easy configuration. Let's talk about in detail regarding TrueEye GUI. So there are a lot of parameters on which GUI works, out of which some of them we will discuss here. The first one is decoding not required. It provides decoded packet, handshake, state machine and command information for transaction level debugging. Its key advantage is easy debugging. Second is configuration. It allows the user to configure the VIP BFMs and create modified tests in a graphical way, bypassing incorrect configs. Its key advantage is easy configuration. Third is attribute searching. Search the required field, that is time, command, error, configs, etc. Its key advantage is easy search. Fourth is error detection. Provides information on errors with their probable cause. Its key advantage is easy error detection. Fifth is automated integration. GUI reduces the man effort by giving the user an option to automate the integration process. Its key advantage is easy integration. Sixth is debug time. GUI reduces the debug time by up to 50% and speed up the process. Its key advantage is save time. Seventh is reduced efforts. Engineers with lesser experience can successfully debug with ease based on useful info from GUI. Its key advantage is resource optimization. Eighth one is package tool. Bundled with the TrueChip VIP, no extra cost is associated. Its advantage is budget optimization. And the ninth, last one but not the least, is the utilization summary. Bus utilization and idle time summary for the performance of the device. Its key advantage is enhanced performance. So there are some examples of GUI. You can see a transaction view which comes in tabular form, as the first column represents the time in a picosecond and the second column represents the rank, as this will be helpful in case of multi-rank. Then comes another column named as channel in order to identify which channel is being processed. Then comes another column named as command. After command column, then comes the row address, column address, and then comes the column address. As you can see, in multiple commands have come one after the another with time scale. First command is mpc zql start command, which comes at 747,003,000 picosecond, which comes then comes mpc zqlh command, then comes multiple mrw commands, mode register write, then comes the activate command with row address and so on. Whereas row address and column address depends upon the command parameters and whether a particular command supports it or not. For example, the mrw command doesn't have a row and column address, so both of them will be blank. Whereas in the case of activate command, row address will be present but column address will be blank in the representation of transaction view. So as the tabular form consists of another page as well as which consists of bank address, bank group, etc. as well. Then comes the transaction view with error information. Like we have run a test and there comes a UVM error. And when we have to see at what time and what error has occurred, so this representation will show each and every information regarding that errors. With its expected and actual means that what was the expected value as per the spec and what value has been received by the monitor at what time scale and at what command, with multiple more fields as per the error, which plays a vital role in debugging easily. On the right hand side you can see the error details that show the error ID that popped out. Actually TrueChip VIP is designed accordingly that the check which are made up of error IDs in order for easy tackle of errors representation which in protocol violation. So like in this, there comes error ID as monitor error E41 with its actual and expected value. On the left hand side of the transaction view, you can see the red colored row that shows that an error has been caused due to this. Now let's talk about another feature of GUI, that is transaction view with fatal errors masked to info. Sometimes there comes an error for a particular scenario and the user wants to mask the error from UVM fatal to UVM info for any reason. The user can also change to warning or fatal. Right now we will talk about error mask to info. So as you can see on the right hand side in the error detail section, monitor error 38 has been masked, which is the light gray color for deselect command, timing at 15867530000 picosecond. So this is how masking can be performed by using GUI. Thank you, ladies and gentlemen.